consistent. All right, hello everyone. My name is Skye Gunasekharan, and today I'll be presenting on my work, A Predictive Approach to Enhanced Time Series Forecasting. So to provide a little bit of context, I've been working on this for the last 2 years. Ever since I was around halfway through my sophomore year, I've been working on this project. And just this Tuesday, it was accepted to Nature Communications, so I'm very happy to have that. I was very proud, and it was a great achievement for my lab and for me and the people that I worked with and my co-authors, so I'd like to just give that as a little bit of context. So every good research project starts with a question, and my problem that I wanted to solve was this. So deep learning models in the last 10 years have been very powerful in the computer vision and the natural language processing domains. However, we haven't seen these same advancements translate into time series forecasting. So why is this a problem? Well, time series forecasting is a very important problem. It's all around us, right? So many types of different data is related to time, a lot of which can be really important, even critical to sustaining life, such as your heartbeat, your blood pressure over time, things like this, right? So the problem was this. The problem was that the classical methods, the statistical methods of doing time series forecasting were on par, if not better, than the deep learning methods, right? So my goal was, how can I elevate deep learning, and how can I use a deep learning framework to elevate the performance in time series forecasting to potentially have better results than the traditional methods that have been around since the 80s and the 90s. So what did I do? I created this framework dubbed future-guided learning. The core idea of future-guided learning is that you use two models. The first model is a teacher. It forecasts the short term, maybe a few steps, few milliseconds in advance. The other model is a student, which makes long-term forecasts. So maybe an hour, 2 hours, 10 hours into the future. So one question might be asking, how do these interact with each other? Well, the idea is that the teacher model, which is forecasting, just a little bit ahead of where it currently is at, can provide guidance to the long-term forecaster, right? Specifically, what we believe is that since the task of short-term forecasting is easier, we can possibly distill some kind of information, distill some knowledge to that student model, right? So, well, your model is able to get 100% accuracy forecasting 1 millisecond, and then you're forecasting 10 seconds, and now it's like 10%, right? So how do you bridge that gap? Well, maybe there's some kind of dark knowledge, some hidden knowledge in that teacher model that you can transfer to the student. So this is our figure 1. It's actually not figure 1. It's actually figure 3 in the paper. They messed it up. I was so frustrated when I opened the Nature manuscript, and I'm like, guys, you put it in the wrong place, but it's okay. So this is our figure 1, and I don't want to go too much into the weeds here, but if you look at part A, you can kind of see a basic idea of what's going on, right? So you have your teacher model that's in the top. If you can see my cursor. Okay, you can see my cursor, good. So this teacher model, right, is having some knowledge of the unseen future that this student model or long-term forecasting model doesn't have access to. And that kind of makes sense, right? I mean, think about it. If you're trying to predict what happens exactly 10 minutes in advance, you don't necessarily know what's going to happen in between that time period, right? So the idea is that the teacher model essentially fills in that gap of knowledge, right? And so the more technical description of how we do this is knowledge distillation. Knowledge distillation, I don't want to go too much into it, but you can see Hinton 2015 if you want to a little bit learn more about knowledge distillation. And so in this paper, we test this framework in two different aspects. We test it in event prediction for seizures, as well as time series forecasting, which is, I would say, the more general kind of task that we wanted to solve, right? So what's our first application? I mentioned seizure forecasting, right? So what's our task? Well, we have some EEG data coming in from a patient, and the idea is, can we predict whether or not this patient is going to have a seizure in this 30-minute interval in the future, right? So what do we do? Well, the teacher is trained, and this might seem a little bit like, what are you doing? I'll explain it, right? The teacher is actually trained to detect seizures as they occur, right? And that can be thought of as forecasting 0 seconds. You're trying to detect what is going on right now. The student, on the other hand, is trained to predict whether a seizure will occur 30 minutes into the future, right? So the idea here is that if you have a well-trained seizure detector model that is able to classify seizures with very high accuracy, the idea is there must be some correlation between the seizure period and the immediately preceding data, right? Because that's what the student is learning. The student is receiving that EEG signal preceding the seizure. And so if it receives this kind of guidance from this teacher model, maybe it can create this correlation, right? So specifically, I guess going even more specifically into our applications, we test this in a patient-specific scenario and a patient-general scenario. Again, I don't want to spend too much time. Patient-specific meaning the teacher is trained per patient, and patient-general meaning this teacher is trained on a collection of just tons of different data, okay? And so the results are really good, actually. In the patient-specific case, which is we hypothesize that the performance is stronger, and it is, it achieves a 44.8% average increase in the AUC ROC compared to the baseline model, right? And this tailored per-patient guidance is quite effective. In the second data set, where the teacher was not patient-specific, it was patient-non-specific or patient-general, the improvement was significantly less. It was only 8.9%, but that's still a nice boost, right? And originally, our hypothesis was that it wouldn't even work at all. So it was actually really good when we were running these experiments that actually there is a boost. Even in this scenario, there's a boost, okay? So takeaway is that future-guided learning improves the prediction accuracy as well as reduces the variance, and as well as, if you can look very closely, there's some of these cases where the baseline model doesn't learn anything, okay? And that with future-guided learning, that the model can perform quite well. Our next application is regression forecasting. So for regression forecasting, we used a differential equation, the Mackey-Glass differential equation. It's a nonlinear dynamical system. I believe it has 5 parameters. It might. I think it should have 5 parameters. So we had a little bit of an issue to do regression forecasting. The issue being we're not able to distill uncertainty, right? The output of a network for knowledge distillation must be a probability distribution. So what we had to do is we had to bin the values. Okay, so we had to bin the values of this continuous time into discrete bins. Okay, and so now instead of the model saying, I believe the point is this, and that's MSE, the model would say, I believe this is the bin, right? And that allows you to have a distribution over bins. Okay, so the teacher would predict the next time step, and the student would predict 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 20 time steps in the future, right? And so results are also very good in this application, where we see that it results in, at least in the best case scenario, in about a 20% reduction in mean square error, a lot of robustness gains, right? This is what we saw in the previous application as well, where there were some situations where the baseline model would not be able to train, and it would essentially collapse, or what we call model collapse, okay? And when using future-guided learning, we were able to alleviate this problem, right? So future-guided learning not only lowers the error, but also makes performance degradation more predictable and graceful as the forecast horizon increases. So, just 1 minute. Oh, okay, good. Oh, yeah. So to summarize, future-guided learning consistently enhances both time series regression forecasting and event prediction in a clinical application. The mechanism comes from 2 key principles: distilling uncertainty from a more confident short-term forecasting model, and using that to aid a more long-term forecasting model, right? And this is inspired, I didn't talk too much about this, but it's inspired by predictive coding theory, which is actually a theory in neuroscience. And you can look at Rao and Ballard 1999 for more of that, okay? So I'll go to my Q&A now, and I want to finish by saying if you want to read the full paper, I have the QR code there. And as well as I do actually teach a course with the neuromorphic computing group, CMPM 118-03. Some people in here are actually in that class. And if you're interested in that, you can look at that. So that's my presentation. Yeah, Q&A? Yeah.
So you talk about improvement in prediction accuracy, but what's the
So the measure we use is area under curve of the receiver operating characteristics. So that sounds like this big complicated thing. The idea is that we want to balance the false positive and the true positive, the true negative, false positive, false negative. We want to balance that. And AUC ROC is a score which balances that, right? Because you can imagine that if I have an hour of data and only 1 second of that is the seizure, and I just keep saying yes, 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 that means the model got 100% accuracy, right? Or got like 99% accuracy, but it's actually not the case. So we use AUC ROC as our metric, which balances that. So it gives a more accurate score of the accuracy. Yeah.
What method was used prior to this method, and how much does this improve on that?
Yeah, so the idea behind future-guided learning is that it's actually not dependent on like a model, right? Like you can use any kind of model. We can use like a LSTM, RNN, CNN. It's not model. It's model agnostic. The core idea behind future-guided learning is how those models actually interact with each other, right? And so they interact with each other by distilling uncertainty from a model that's trained on a different data regime entirely, or in this case, in the future. Yeah. I will say there is some information that is very closely related to the work we do. It is called, in the classical time series forecasting case, there is this like reset mechanism. I don't have the name of it off the top of my head, but the idea being like you test the model's performance on like a small part of the data, and then depending on how it performs, you can retrain it. And so that was something we also talk about in our paper and the related works. Yeah. Do you want to?
Just a follow-up.
Of course.
Another question. I
Yeah.
usually have a couple of questions.
No, it's great. I love this.
So is this something where you're starting off looking to how can we do predictions of seizures, or are you using seizure prediction data to test the model? What was the impulse for?
Yeah, so actually this was inspired by some previous work that my professor did with his friend at University of Sydney. And so there was a paper where they used a seizure detector model to actually supervise a prediction model. And so I know it sounds similar. The way they did it was a little bit different. So they had the seizure detector model actually tell the seizure predictor model when is the seizure, right? So it would literally be the label, right? It would be the label creator. And so I said, let's take that a step further and let's integrate the information more directly. And so then that's how we got to seizure prediction. Again, more of a communication thing. We didn't want to say, oh, this works on seizure prediction. We want to say this works in clinical forecasting, right? Like we want to make our audience like a little bit more broad. So that was a kind of a choice that we made for the paper. Yep. Yeah. Oh, someone. Oh, yeah.
So is the seizure prediction binary?
Yes, it's binary. So there's two outputs.
So is there, how do you think this algorithm would do again?
So the student model is trying to predict, its outputs are, it has two choices, right? Either this is a pre-ictal. Pre-ictal means pre-seizure, or it's inter-ictal, meaning there's nothing going on, right? And then the detector model can choose between ictal, like there is a seizure, or inter-ictal, meaning there is no seizure. The idea is that we want to align the ictal, right, the activation of ictal and activation of pre-ictal together, which is why we align them.
Okay, that's what
Yeah, the idea being that if there's a strong correlation with the seizure, there's also a strong correlation with the period before the seizure. Yeah. Okay, good.
Leave it there if you could, because I want to point some stuff on some of your slides.
Oh, yeah, of course.
Okay. Also, first thing, you left out an important step. Oh, to clap and it's done. Okay, so this is.